Hello, my name is Isabella Habersky. I'm a fourth-year chemical engineering student at Michigan Technological University, currently enrolled in CM 3510 Kinetics. Today I'm going to be solving a problem from Elements of Chemical Reaction Engineering, 4th edition by Fogler. The problem I'm going to be solving today is 7-7, specifically part B. So our problem is, one of the major reasons for engine oil degradation is the oxidation of the motor oil. To retard the degradation process, most oils contain an antioxidant. Without an inhibitor to oxidation present, the suggested mechanism at low temperatures is the following. As you can see, there are several steps, several intermediates in this mechanism. I2 is going to be the initiator, and RH is the hydrocarbon in the oil. So RH is what we actually care about, but that is going to come later. So when an antioxidant is added to retard degradation at low temperatures, the following additional termination steps occur. In part B, we need to derive a rate law for the rate of degradation of the motor oil in the presence of an antioxidant for low temperatures. So we are going to need those two final termination steps. Alright, so two things. One, I write my zeros as a circle with a line through it, so just so you don't get confused when those pop up. And I like to set up my problems in sections. So given, need, and solve. I like to collect all my information. Our information is our mechanism. It has all of our components listed, our intermediates, and it also has our K values. And for need, all we need to know is the rate law for the rate of degradation of the motor oil. So that's going to be RH, because that is the hydrocarbon in the motor oil. In order to solve this problem, we need to apply the pseudo steady state approximation. So the rate of change of concentration of intermediates with respect to time is going to be 0. Our intermediates are I dot, RO2 dot, R dot, and A dot. Okay, so we are going to begin by getting our rate laws for our intermediates and solving for the concentration of them. So I'm going to explain how I get the first one, and for the first rate law, I should say, you can see how I rearrange the equation. But I'm only going to explain the first one, and the other ones will be the same idea. So for this first one, our intermediate is the I radical, which is only present in the top two equations. So that's the only two we need to worry about. So we have K naught for the first one and Ki for the second one. So when we're looking at these equations, in order to find our rate law, we're going to have, for the I radical I should say, it's going to be 2, because there's a coefficient of 2, and then times K, in this case K naught, and then times the concentration of I2, because that is what is our reactant. Alright. And then for the second one, we need to have our coefficient again. In this case, it's going to be -1. And then we need to multiply that by our K, in this case Ki, and then by our concentration of our I radical, and also the concentration of RH. We're going to add these together like so, and then solve for the concentration of I radical. Alright, so we have also done the same process for our concentration of R and A radicals. However, it's going to be a little bit different for our concentration of RO2, and that's just because we're going to have to do some substitution to get there, and then another equation that we'll get to. So once we find our rate law for RO2, it's actually going to turn out we have a lot of the concentration of the other radicals in here. So we're going to actually substitute those into our equation. We're going to get the following, but we want to get negative rate of RO2. So we got to multiply -1 on both sides. So we're going to get this equation here. Only thing that has changed is our signs have been changed to the opposite. So now we can finally solve for the concentration of RO2. And this is going to be a quadratic equation because if we look at this, we can take our concentration of RO2 to be x, and since there's a squared term, that's going to be our x squared term. And then, as you can see, I've labeled all of the rest of the sections of the equation, and we're going to use our quadratic formula in order to solve. So, as you may recall, this is x equals -b plus or minus the square root of the quantity of b squared minus 4ac all over the quantity of 2a. So subbing in these sections of the equation, we are going to notice we actually haven't gotten rid of all of our radicals. So we have to substitute the concentration of I radical again, so that way we can get rid of all of the intermediates. Alright, so now we have our concentration of RO2 radical. Now that we have all of these concentrations, we now need to go back to our original focus, which, if you can remember, is going to be RH, our hydrocarbon in our motor oil. So we have to find our rate law, similar to how we found the rate laws for all of our intermediates. Okay, so now that we have our rate law of RH, we notice that we have two intermediates in here. We have the I and RO2 intermediates. We cannot have that, so we're going to sub both of them in. And finally, once we've done that, we don't have any more intermediates in here. So this is going to be our rate law of the degradation of motor oil, boxed below. I hope you have a good day.